Here in section 6.5, we're going to talk about circular functions, their graphs and properties. Our first objective is given coordinates on the unit circle, find its reflection across the x-axis, y-axis, and origin, talk about those 6 trigonometric function values for any real number where coordinates are on the unit circle, and then find function values for any real number using a calculator, assuming they mean trigonometric function values, and then graph the 6 circular functions and state their properties. We haven't graphed them before, so it's going to be something new. So quick review. What do we know about the domain of the 6 trigonometric functions? So they each take in an angle, so like sine of theta. If I was to write this as a function, I might write f of theta equals sine of theta, or I could have another function g of theta equals any of the trigonometric functions. So for example, secant of theta, doesn't matter which of the 6, there's all 6 of them, of course. I just wrote down 2. But they have the commonality that they take in angles, and so if I want to talk about the domain, I want to talk about what kind of things can be inputted for those angles. And so we have talked about coterminal angles and angles that rotate all the way around, so they can be very large. We've also talked about angles that go in the negative direction, so they can also be large negative. So it's actually any positive or any negative. So the domain is going to be all real numbers for these. Negative angles or positive angles both have application. The domain is going to be all real numbers or the interval negative infinity to infinity. Any value can be an angle. Okay? So on the unit circle, where the radius is 1 unit, what is the relationship between an angle and the arc length swept out by that angle on a circle? Remember that if we're on the unit circle, the arc length was going to be equal to the measure of the arc length in radians. So whatever your angle happens to be, the arc length was equal to the angle because it's a unit circle specifically, so this value is 1. So on the unit circle, theta is equal to s, the arc length, as long as theta is in radians. And s is the arc length. Now, we remember in the previous section that if this wasn't a unit circle, it was a circle with some other radius, there was a formula for computing theta in terms of arc length. I think it was theta equals s divided by r. But if it's on the unit circle, I'm dividing by 1. So the angle is the arc length on the unit circle if you're in radians. Okay, so very important, the connection between s and theta. Oh, I just talked about that. And if we measure all angles from the positive x direction, then the point on the unit circle with coordinates x, y that creates an arc length s defines the 6 trigonometric functions for this angle. Okay, so here's our angle, here's our arc length, and so we are imagining the triangle. If I drop down a straight line right here, I'm imagining this triangle connected to that ordered pair, and since x is the horizontal distance, it's the adjacent, and y is the vertical distance up, it's the opposite. And so just using what I already know about the trigonometric functions, about opposite over hypotenuse for sine, since I'm on the unit circle, the hypotenuse is 1, so I can just say sine of s is 1. You can interchange s with theta here since they are equivalent because this is a unit circle. So sine of theta is equal to y, sine of cosine of theta is equal to x because it would be adjacent over 1, and so on. So all of these are true on the unit circle. So we're going to build on this as we get to the next page, and further in this section we're going to talk about any trigonometric function is going to have a domain of all real numbers, and these are all called circular functions because of the way that they're defined based on that unit circle. Alright, we will look at those some more in just a moment. First, on the next page, we have the unit circle. So the unit circle has, we saw many of these facts in a table where we talk about the sine of, say, 30 degrees and cosine of 30 degrees. And we made a table that had all the values, sine, cosine, tangent, secant, etc. of 30 degrees. The unit circle organizes this information a little differently and a little more efficiently. They're not going to tell me the sine, cosine, etc. values for each of these angles. Instead, they're going to give me the ordered pair, the xy coordinates. Now, remember from the previous page that the sine is the y value and the cosine is the x value. So those ordered pairs, x comma y, are the cosine value comma the sine value. So we'll make a note of this here as well. Each of these ordered pairs on the unit circle is the cosine of the angle comma the sine of the angle. So if I wanted to find any of the trigonometric values, I can read them off the unit circle. I can read off the cosine value and the sine value for the 30 or the pi/6 degree. Again, I have the degree measure and the radians, and I have them listed for each of these. Now, we do, at the bottom of the page, see the note that we do need to memorize the unit circle. You're going to be using it all the time here in this chapter and in calculus as well. So we are going to work on that, memorizing the unit circle, but we are going to be smart about it. We're going to use symmetry and patterns to do so. So if we take a look at some of the things we notice, it's really unnecessary to memorize the first quadrant because of symmetry. So if I look at the first quadrant, it's mirrored over here in the second quadrant. The only difference is that the x-coordinates become negative. And then if I look at the first quadrant again, I can mirror down. The only difference is the y-coordinates become negative. And then, of course, in quadrant 3, both x and y are negative. Okay? So the first quadrant here is the most important in terms of memorizing the unit circle. Okay. After that, symmetry comes into play, and we can get all the rest. So focus on that first quadrant. And again, the 30 and the 60 have similarities. They have the two values, 1/2 and square root of 3 over 2, or square root of 3 over 2 and 1/2. And then pi/4 is actually the easiest one to remember because they're both root 2 over 2. Okay, so you can probably remember the pi/4 or the 45 degrees is root 2 over 2, root 2 over 2. For these two, remember whether it's a tall triangle or a short triangle. So the 60 degree is the tall triangle, so it has the y is the height as the larger value, root 3 over 2. And the pi/6 or 30 degree is the long triangle or short triangle. So it's long, so it has a larger value than root 3 over 2 in the x-coordinate. That's how I keep those memorized because I can see those triangles when I'm thinking about that angle. Okay. So those two triangles help me remember which one's which. All right. So I'm going to look at the next page and we'll come back to our unit circle here. So for a point on the unit circle, for any point x comma y, we know that the x is equal to the cosine of theta and the y is equal to the sine of theta. So we mentioned that on the previous page. Okay. So in example 1, I want to determine any other possible coordinates for a point on the unit circle with the given coordinate. All right, so if the x value is 1/2, what might be another pair for that? Okay, so what we are thinking about is that there are going to be two for these, right? So an x value of 1/2 is going to occur in quadrant 1, but x could also be 1/2 in quadrant 4. So it could be either square root of 3 over 2, positive or negative in the y-coordinate. So determine other possible coordinates for a point in the unit circle with a given x-coordinate. They could be either 1/2 comma square root of 3 over 2, or they could be 1/2 comma negative square root of 3 over 2. Draw a sketch of each situation showing the possible points. So on my unit circle, that's a really bad circle, but we'll pretend it's a good circle. On my unit circle, I have the 1/2, which is my 60 degree angle, and then I have the negative square root of 3 over 2 down here at the negative 60 degree or at the 300 degree if you're thinking it in degrees, or again at the pi-thirds or the negative pi-thirds, again the positive for that's 5 pi-thirds. So those are the two that we are using here. Okay, let's take a look at the next one. Now draw a sketch of each situation showing possible points. Okay, determine other possible coordinates. This one is not a point that's on the unit circle, so it's not going to have a special angle like 30, 45, or 60. It's got a y value of negative 2 over 3. So let's determine the other possible coordinates and draw a sketch. I'm going to draw my sketch at the same time and then determine the other possible coordinates. So my sketch on the unit circle has a y value of negative 2/3. So we're going to be looking at y's of negative 2/3. So y values right around here and here. So the same y value is going to have one positive x and one negative x. Okay. Now, I know that it's on the unit circle, and so I can solve for the x value, and we'll just take a look at one of these first with this triangle. I know that it's the unit circle, so the radius is 1. So I know that x squared plus negative 2/3 squared equals 1 squared. So x squared equals, I'll write first of all, x squared plus 2 squared, that's 4, 3 squared, that's 9, x squared plus 4/9 equals 1. So x squared equals 1 is 9/9 minus 4/9 is 5/9. Square root of both sides, I'll get positive and negative the square root of 5/9. So positive and negative the square root of 5 over 3, since the square root of 9 is 3. Okay. So those are the two x values that correspond with each of these. So determine other possible coordinates. Those are the two other coordinates. If I could write the two ordered pairs, they will be negative square root of 5 over 3, comma negative 2/3, and square root of 5 over 3, comma negative 2/3. All right. Now, I could have done this the same way, don't forget. 1/2 happens to be on the unit circle already, so I already know it matches up with the square root of 3 over 2, but where did that come from? It came from that same process of the Pythagorean theorem. We just did that in a previous exercise when we were talking about how to create the 30, 60, 90 triangle, so we don't need to reinvent that every time. It's on a special angle. It could be done though. Okay. All right, and then the last part here, part C, we're looking for a place on the unit circle where the x value is negative 1. And so when the x value is negative 1, we have to be right there on the x-axis. The radius has to be equal to 1 as well. And so the only possible ordered pair for that is negative 1, 0. I don't need to do the Pythagorean theorem. If I wanted to, it would come out the same way. I know that it's a unit circle, so the radius is 1. I could set up negative 1 squared plus y squared equals 1 squared, but we're going to get y equals 0 from that as well, right? But I can see from my diagram as well that if I'm on the x-axis, I'm going to be at the point negative 1, 0. Okay, I'm going to pause here, get to the next video.